Hey guys, I hope you all are doing good. In this lecture, we will be starting with a very new topic, which is binary relations, right? So we will cover this topic in like 3 to 4 lectures. Before this, we covered the proofs in detail. So if you haven't covered that yet, I would highly suggest you cover it first, right? And also, it would be very important that you have a good understanding about sets before moving on to binary relations, right? So let's start with understanding what is a binary relation. It is basically a binary relation is from set A to set B is a subset of the Cartesian product of A cross B. That means a relation is just a set of ordered pairs A, B, where A is an element of A and B is an element of B, right? This is very easy to understand. So let me give you an example, right? It is a binary relation from set A to B is a subset of the Cartesian product. So what I'm trying to say is, let's say A is a set 1, 2, 3, and B is the set A, B, C, right? What is going to be the Cartesian product? So if I do the Cartesian product, if you remember, then it is basically a set of the tuples, right? Where elements of A will be on the left hand side and elements of B will be on the right hand side of the tuple. So I get 1 comma A, 1 comma B, 1 comma C, and so on, right? And this way I will have exactly 9 elements, right? Because it's elements of A multiplied by elements of B, which is equal to 9, right? So this is the basic idea. And the binary relation is going to be a subset of the Cartesian product. So what I'm trying to say is that, let's say I take the subset, right? If you say 1A, 1B, 1C, maybe the relation is 1A, 1B, and let's say it's 2 comma C, right? So what we are trying to say is that there could be relation which is going to be a subset of their Cartesian product, right? That means a relation is just a set of ordered pairs. So if you look at it, this is a set of ordered pairs where A is an element of A and B is an element of B, right? So this is a set of ordered pairs, and if you look at it, then 1, 1, and 2 are elements of the set A, and A, B, and C are elements of the set B, right? So I hope you understand, have a basic idea about what is a binary relation. It's just a different definition, but I think the concept is very simple to understand, right? Okay, notation. Let's try to understand the notation. We notate it as relation is a subset of A cross B. So I hope you understand the definition, right? The notation of the subset. And we say the tuple A comma B is an element of R, right? So let's try to understand this. The tuple is an element, right? In this case, because these tuples are basically the elements of this set, right? So is an element of this relation. We say A is related to B or A R B, right? So this is a very important notation to understand. So whenever you form a binary relation, right, you could be given a binary relation in a question, or you might be asked to form one relation, right? This is the notation you might use, right? So A related to B, where A is going to be the left element of the tuple and B is going to be the right element of the tuple. So let's take an example, right? This is A cross B, which is going to have 9 elements. This R is a subset of the Cartesian product, and the notation is 1 related to A. This can also be written as 1RA. I can also write 1RB and 2RC, right? So this is the basic understanding about what is a binary relation, right? So I hope you're able to understand how the binary relation works. Now, just before I move on, I want to give you a basic difference between what is a function and what is a binary relation, right? So if you remember, in a function, it also was a set of tuples, right? So for example, it could be a set of tuples, but if you remember, there was a one basic rule that we had, right? One very important rule that we had. So one element of the domain can only point to a single element in the codomain, which is what I'm trying to say is, in a function, f of 1 can only be a unique value. F of 1 equal 1, f of 1 equal 2. This is going to be incorrect, right? So if you remember, a function is also a binary relation, but with an additional condition on it, right? So I hope you're able to understand it. And binary relation is kind of like the general thing that we use. Okay, so I hope you're able to understand what is a binary relation. Now let's try to understand how to classify a binary relation based on different types. Okay, so now let's try to understand the different types of binary relations in detail, right? So basically what we are trying to do is we are trying to classify relation on different types. So these are the four different types. A binary relation can be reflexive, symmetric, antisymmetric, and transitive, right? So before I start, one important thing to understand is all of these are defined on the Cartesian product of a set to itself, right? So what I'm trying to say is all of these, right, they are defined on, let's say if set A is 1, 2, 3, then they're defined on A cross A. Basically, they are defined on the subset uh, of a Cartesian product of a set to itself, right? So maybe it could be A cross A, it could be a set multiplied by itself, right? But it has to be, they are the same set. Okay. So let's try to understand each one in detail of how they work. I'll also write down the relation of A, 1, 2, 3 with itself. So A cross A is basically going to be 1, comma 1, 1, comma 2, 1, comma 3, 2, comma 1, 2, comma 2, 2, comma 3, 3, comma 1, 3, comma 2, and 3, comma 3. So let's first try to understand what is going to be the binary relation, right? So if you understand the definition, a binary relation is a subset of the Cartesian product, right? Now it could be the entire set itself, which is this, it covers all these relations, right? Or maybe it could be just a subset of a few elements, right? So for now, what I'll say is, I'll say the relation is, I'll take three of the elements in this set. I'll say 1, comma 1, 2, comma 2, and 3, comma 3, right? For now, let's try to just keep in mind that this is the relation defined. So let's start with understanding what is a reflexive relation, right? A relation is reflexive if for all the values A in the set A, right, the element A comma A is an element of the relation R. Okay, so I hope you understand what this means. What I'm trying to say is for all the elements A which are elements of the set A. So for example, I'm saying is for all the values 1, 2, and 3, right? This tuple A comma A is an element of the relation R. Okay. In very simple words, for each of the relation, for each of the values in the set, in the relation, they should be related to themselves, right? So if you look at this relation, right, 1 is related to itself, 2 is related to itself, 3 is related to itself, right? These are the three unique values that I had in the set, and they are all related to themselves, right? Hence, I can say that this is a reflexive relation. Okay, so just a quick summary of what is a reflexive relationship. Whenever you are trying to figure out whether a relation is reflexive, right, what you need to see is you need to look at the elements in a set and you need to see that in the relation they are all related to themselves. So let's say if I had a set B, 1, 2, right, and if I had the relation 1, comma 1 and 2, comma 1. Okay, so do you think this is a reflexive relation? You can pause this video for 5 seconds and try to figure it out. Okay, so the answer is that this is actually not a reflexive relation, right? Why? Because even though 1 is related to itself, 2 is not related to itself, right? Hence, this is not going to be a reflexive relation. So I hope you understand the basic definition of what is reflexive. This is the most easy to understand. But the basic point is for all the values in the set, they should be related to themselves in the relation, right? Okay, moving on, let's try to understand what is a symmetric relation. So if the tuple AB is an element of the relation, so if A is related to B in the relation, then B should also be related to A in the relation, right? So what we are trying to say is, if I have the element 1, comma 2 in the tuple, so I'll try to give an example of it. Now let's try to change this relation, right? Let's say my relation was 1, comma 2, 2, comma 1, 3, comma 2, 3, comma, sorry, 2, comma 1, or I should say 2, comma 3. Okay, so if you look at this relation, right, according to the definition of if a relation is symmetric or not, if the tuple AB is an element of R. So let's take a look at all the tuples that we have, right? If tuple AB, so I see that 1, 2 tuple is an element of the relation R. Then, according to the condition, the tuple BA should also be in the relation, right? So basically, I see 1, 2 in the relation. Now, what I'm supposed to check is I'm supposed to check whether 2, 1 is also in the relation. So I see 1, 2 is in the relation, 2, 1 is also in the relation, right? Hence, until now, if we just cover these two elements, until now, this is a symmetric relation, right? Moving on, if I see the tuple 3, 2, I need to find 2, 3 as well in the tuple, 2, 3 as well in the relation, right? And I see that it is also in the relation. And hence, this is going to be a symmetric relation. So the basic point is, if a tuple AB, right? Now, one thing to understand is, it is not that these A, B are unique values. It could be that they're both the same value, right? So if AB tuple is an element of the relation, then the opposite should also be in the relation, right? That is how it will basically be symmetric. So in this case, 1, 2 is in the relation, 2, 1 is also there, 3, 2 is in the relation, 2, 3 is also there, right? Okay. Now let's take a look at another example, right? Let's say the relation is 1, 2 and 1, 1. Okay. You can pause this video and try to figure out whether this is a symmetric relation or not. Okay, so this is not going to be a symmetric relation, right? Why? If I look at this element, right, 1, 2, I cannot see 2, 1 in this relation, right? And if a relation is symmetric, then the opposite should also be there. So this is not going to be a symmetric relation, right? Okay. Also, this can also be the case. So if I have 1, 1, 1, right? Since 1, 1 is there, if I take the opposite, it would still be the same element, right? Which is present in the relation. So if I give you another example, right? Take a look at this question. 1, 1. If I ask you the question, do you think this is symmetric or not? What do you think would be the answer? So the answer in this case again would be that this is symmetric, right? So you just need to check the condition and look at the condition, what it's trying to say. What we are saying is, we are saying if AB tuple is an element of R, then the opposite should also be there. So I see 1 is related to 1 and 1 is related to 1, right? If you just switch the elements, then it is the same tuple. Same is with 2, 2 and same is with 3, 3. 3R3 is equal to 3R3, right? Doesn't matter if I move this 3 to this side or this 3 to this side, right? So I hope you're able to understand the concept of what is symmetric. Moving on, let's try to understand what is antisymmetric. So just a quick thing to understand is, right, you need to check the first condition. If this condition is true, then only you need to check for the next condition. If you find out that this condition is not true, then you don't have to worry about the second condition, right? Yeah. So antisymmetric, if AB is an element of R and BA is also element of the R, then A is equal to B. So if you try to read this statement, what we are trying to say is that at most, an element should be related to itself and not any other element, right? So what we're trying to say is, let's say I have relation is 1, 2, 2, 1 again, right? Okay, let's try to understand whether this is an antisymmetric relation or not. We are saying if AB is an element of R, so I see the first, let's take a look at this first tuple, right? 1, 2 is an element of R, and the condition is, and BA is an element of R, right? BA is an element of R, then A should be equal to B. But if you look at it, 1 is not equal to 2, right? Hence, this is not going to be a antisymmetric relation, but it is going to be a symmetric relation in this case. Let's take a look at another example, right? Okay, I'm going to take the reflexive example one more time. So let's say I have 1, 1 and 2, 2, right? Okay, let's check the condition once again. If AB is an element of the relation R and BA is an element of the relation R, then A is equal to B. So I see 1, 1 is an element of R, right? 1, 1 is also an element of R, which is, I can move this tuple, I can switch the elements 1, 1 to the other side because they're basically the same element. Then A is equal to B, right? And you see that 1 is equal to 1 and 2 is equal to 2. So if you're not able to understand what I'm trying to say, that's totally fine. But my basic point is that if a relation, you see that 1 is related to 2, there are two elements, right? In a tuple, 1, 2 is present, and 2, 1 is also present. But since they are not equal to each other, it is not going to be antisymmetric. So the condition you are trying to see is that if two elements are related to each other and they are not equal, then it is not going to be antisymmetric, right? Okay. Moving on, let's try to understand the final one, which is what is a transitive relationship. So if A is related to B, right, and BC is related to R. So I hope you understand there are two ways to say this, right? I can say B is related to C, or I can also say that the tuple BC is an element of the relation R, right? So what I'm saying is, if the tuple AB is an element of relation R and BC is an element of relation R, then AC should also be there. So let's take a look at this example. Let's say this time the relation is 1, 2, 2, 3, and 1, 3. So let's try to understand whether this satisfies the condition of transitive relationship. So I'm saying if A, B is an element of the relation R, so let's first start with this side, right? Okay. So I see A, B is an element of the relation R. B, C is also there. B, C is also there. 2, 3 is also there. Then according to the transitive condition, then the first element should be related to the third element, right? So A, C is also there. So this is A, B, this is B, C, and this is A, C. So the basic idea is if 1 is related to 2 and 2 is related to, let's say, another element, then the first element, which is A, should be related to that third element, right? Okay. So I hope you were able to understand all these concepts in detail. If there are any doubts, then don't worry about it. We will cover a few questions to understand each one of these in detail. Okay, so I've given a bunch of questions on the board, right? These are not that tricky questions. If possible, I want you guys to solve these questions and then, so you can pause this video, solve these questions, and then I'll try to solve them for you guys. Okay, so let's start with question number 1. Let A be the set of 1, 2, 3 and define the relation R, which is equal to this relation over here. So we are supposed to figure out which of the following properties are does R satisfy, right? So by now, I hope you understand all the definitions and what is the meaning of each and every classification, right? So what is reflexive, what is symmetric, antisymmetric, and transitive, right? Okay. So starting with the first one, let's try to understand whether this is reflexive or not. So the very important thing to understand was if a relation is reflexive, then for all the elements in A, they are all related to itself, right? So let's take a look at all the elements in A, right? I see 1, right? I need to find 1 is related to itself. So it is over here, right? That is satisfied. 2, 2 is related to itself, and 3, 3 is also related to itself. Even if one of these three was missing, this wouldn't be reflexive, right? But in this case, it is actually going to be reflexive, right? So I hope you're able to understand. So basically what we do is for all the values in the relation, they should be related to itself in the relation in order for it to be reflexive, right? So 1, 2, 3, all of them are related to themselves. Okay. Second one, let's try to figure out whether this is symmetric or not. So if you remember, it is very important to understand the condition, right? What does it say? It says if A is related to B, then it has to be the case that B is related to A, right? So let's take a look at this example, right? Let's take a look at from the first one until the very end. I see 1 is related to 1 and 1 is related to 1, right? So if I move the one element upside down or to the left hand side, then it would still be the same tuple, right? So these three satisfy the symmetric condition. Let's take a look at the fourth one, right? 1 is related to 2. It says, according to the symmetric definition, if A is related to B, then B should also be related to A, right? So I see 1 is related to 2 and 2 is also related to 1. Hence, the condition has been satisfied, right? But think about it. If I had removed this condition, then this wouldn't be symmetric anymore. But in this case, it is also going to be symmetric. Okay, third one, let's try to understand whether this is antisymmetric or not. So according to the definition of antisymmetric, if 1 is related to 2 or A is related to B and B is related to A, then A should be equal to B, right? But in this case, I see 1 is related to 2, 2 is related to 1, but 1 is not equal to 2, right? Hence, this is not going to be antisymmetric. Moving on, let's try to understand whether this is transitive or not. Okay, this might be some tricky to understand. You might assume that this is not transitive, but it actually is, right? So let's try to understand how. So according to the definition of transitive, if A is related to B, right? So if there's a tuple A, B in the relation, and there's a tuple B, C in the relation, then there should also be the tuple A, C in the relation, right? So you need to always understand what is the if condition, and if that if condition is true, then you need to figure out the next condition, right? So it's kind of like this, right? So P then Q. If you figure out that this P condition is true, then only you need to figure out whether this Q or not. If this P condition is not true itself, then you don't have to worry about the Q condition. It is still going to be true, right? So let's try to understand how this works. So let's try to take a look at this, right? I see 1 is related to 1, so we don't have to worry about the transitive portion in this case. 2, 2, 3, 3, we don't have to worry about it either. But let's take a look at this, right? 1 is related to 2, so A is related to B, B is related to C, right? In this case, we will kind of assume that this is transitive. 1 is related to 2, 2 is related to 1, and 1 is related to itself, right? So if you think about it, this can be A, this can be B, this can be B, this can be C, and this can be A, this can be C in this case, right? And another example could be this is A, this is B, 2 is related to 1, 1 is related to 2, C, and 2 is related to itself. And we see that both the conditions are present, right? So what was the definition of transitive again? If A is related to B, B is related to C, then A should be related to C, right? And in this case, we can figure out that all these conditions have been satisfied. Okay. But if I make one change, right? If I remove either 1, 1 or 2, 2, then this wouldn't be symmetric anymore, because 1, 2, 2, 1 would be present, but 1, 1 or 2, 2 would not be present, right? So hence, in this case, this is going to be transitive as well. Okay. So if you're not able to understand it, I would suggest that you can pause this video or try to rewatch this video one more time, right? Okay, moving on, let's try to understand. Construct a relation A on A that is both symmetric and transitive, but not reflexive, right? So let's try to understand this, right? This is going to be an easy question. Whenever a relation is reflexive, that means all the elements should be related to themselves. So the only thing that I need to prevent in this case is I need to prevent all the elements being related to themselves, right? So I've been given a 1, 2, 3, right? Relation. I'm going to just give you the relation and I'll try to explain what I'm saying, right? So I can say 1 is related to 2, 2 is related to 1, 1 is related to 1, 2 is related to 2. And this could be my final answer. Okay, so let's try to understand how this is symmetric and transitive, but it is not reflexive, right? Okay, so how is this symmetric? If you think about it, 1 is related to 2, 2 is related to 1, right? A related to B, B related to A. So both the opposites are present. Same as 1 is related to 1 and 2 is related to 2, right? So we don't have to worry about the symmetric part for this one. So this is symmetric, right? That condition has been satisfied. Transitive, let's try to understand how this is transitive, right? So if you remember from this case, right, 1 is related to 2, 2 is related to 1, and 1 comma 1 is also present, which can be kind of treated as a comma C, and 2 1 and 2 1 1 2 is present, and 2 2 is also there, right? Again, 1 C kind of portion. So the transitive condition is also satisfied. But in the set of A, But in the set of A, I had three elements, right? So I had 1, 2, and 3. But if you look at it, I have 1 related to itself, 2 related to itself, but not 3 related to itself, right? Hence, in this case, this is going to be symmetric and transitive, but not reflexive relation. Okay. So moving on, let's try to understand question number 3. Given A, 1, 2, and B is equal to AB, R is equal to 1A, 1B, and 2A. Is R a function from A to B? So if you remember in the starting of the video, I was talking about this concept, right? So this is a relation, right? There's no condition on the relation, right? We don't have to worry about something that would turn this into not a relation. But when we talk about a function, right, I told you that there's a specific condition that we understand in a function. So if you think about it, if this was a function, right, f, let's say if I change this to f equal to 1a, 1b, 2a, is this going to be a function or not? And the answer is no, right? Why? Because one is related to a and one is also related to b. So this is kind of like one has an arrow to a and one also has an arrow to b in the function, which is not possible, right? In a function, one element of the domain should only point to a unique value in the codomain. It cannot point to multiple values, right? Okay, so I hope you were able to understand this question is R a function, and the answer is going to be no. Moving on, let's try to solve question number 4. Given A is equal to 1, 2, 3, suppose a relation R on A is reflexive, symmetric, and transitive. You are only given two pairs, right? 1, 2, 2, 1. List all the other pairs that must be added to satisfy the three properties. Okay, so let's try to think about it, right? Let's start with the first one. How can I make this reflexive, right? This is very easy to understand. I need to add all the pairs related to themselves. Since A has three elements, 1, 2, 3, I can add I can add 1, 1, 2, 2, and 3, 3, right? I already have 1, 2, and 2, 1, right? Which has been given to me by the question. So I made this reflexive. I added 1 is related to itself, 2 related to itself, and 3 related to itself, right? 1, 2, and 2, 1 is already present. So second one, let's try to understand how to make this symmetric. So if you look at it, this is actually already symmetric, right? Why? Because 1 is related to 2 and 2 is related to 1 is present, and we don't have to worry about the symmetric case for these three elements, right? Okay, so this is symmetric already. Now let's try to understand whether this is transitive or not. So 1 is related to 2, 2 is related to 1, 1 is related to itself is also present. Same again, 2 is related to itself is also present. So I hope you understand this concept from these two questions that we covered, right? So this is also going to be transitive as well. That basically means I don't need to add any more elements to this relation. This is going to be satisfying all the three conditions, right? So hence this relation is reflexive, symmetric, and transitive. Okay, so I hope you were able to solve all these questions. If there was any doubt, you can leave me a feedback in the comment section, and I'll see you guys in the next lecture.